Riemann sums and finding the area under a curve using geometry was an excellent introduction into Calculus 2. But to really get into the meat of Calculus 2, we need to start talking about antiderivatives. An antiderivative is exactly what it sounds like. It's the opposite of the derivative. It's like undoing the derivative. Just like multiplication and division undo each other, addition and subtraction undo each other, natural log and e undo each other, antiderivatives and derivatives undo each other. 5.4 starts off with some properties that we're probably kind of assuming that you know, and that you're probably kind of understanding just based on what you've learned before about derivatives. So they're a little bit intuitive. Basically, we can separate them if we wanted to, if we have two functions. We can multiply by our constant on the outside, and we can break it at some point. If we want to go from a to b, we can go from a to c of f of x dx, and then from c to a of f of x dx. This last one becomes really important when we have negative area. And sometimes negative area is okay. It takes away from like our work. But if we're looking for net displacement or how much total work we've done, net work, then we have to figure out the negative and then add it to the positive. We'll be doing some more of those, so don't worry too much about that. All right, so in example 1, you don't really have to write it out this way, but I'm going to write it out for the sake of it showing you this. It goes from 0 to 1 of x squared dx plus the integral from 0 to 1 of e to the x dx. So this is 1/3 x cubed from 0 to 1 plus e to the x from 0 to 1. So that's 1/3 plus e to the 1 plus e to the 0. Anything to the 0 power is 1. So let's see, that's 1/3 plus 1, or 4/3, plus e to the x. Now, of course, if you didn't want to break it up, you could do that all in one shot. It's really your personal preference and what you feel comfortable doing. Here we have a constant of 3. We can pull that 3 out and make it 3 times the integral from 1 to e of 1 over x dx. And again, hopefully you know 1 over x is ln. So it's going to be 3 times ln of x evaluated from 1 to e. So that's 3 times ln e minus ln 1. The natural log of e is 1. The natural log of 1 is 0. So it's just 3 times 1, or 3. Now here is one that we're going to need to use that splitting up problem. So if I'm asked to find the area under the curve between 0 and 15 of f of x dx, what I'm actually going to need to do is first find the area from 0 to 10 of f of x dx, then find the area from 10 to 15 of f of x dx. All right, so let's plug in what we know. From 0 to 10, we're going to get x squared dx. And then from 10 to 15, it's just 100 dx. So the antiderivative of x squared is 1/3 x cubed from 0 to 10, plus the antiderivative of 100 is 100x, and we're going to evaluate that from 10 to 15. So let's see, that's 1/3 times 10 cubed minus 1/3 of 0, so that just goes away, plus 100 times 15 minus 100 times 10. And if I reduce that, I'm going to get 2,500 thirds. Now we've talked about the mean value theorem for differentiation. Now we have a mean value theorem for integrals. So the mean value theorem for integrals says if a function f is continuous on a closed interval a to b, there's a real number u, which is between a and b, for which the integral equals the average value, f of u times b minus a, which is very similar to how we saw it happen in the derivative side. All right, so let's take a look at this. So we know by our mean value theorem that if we're going to go from 2 to 6 of x squared dx, then there's some f of u between 2 and 6 such that f of u equals 6 times, the integral equals f of u times 6 minus 2. All right, so let's do that. That's 1/3 x cubed between 2 and 6. So 1/3 of 6 cubed minus 1/3 of 2 cubed. So 6 cubed is 216 thirds minus 8 thirds. So that's 208 thirds. And that has to be the same as f of u times 6 minus 2. And let's see what f of u is. So f of u, if my function is x squared, then my f of u is going to be u squared. And 6 minus 2 is 4. So 208 over 3 equals 4 u squared. So now we're going to solve this for u. Again, hopefully you're noticing that this is very similar to the mean value theorem for derivatives. So let's see, that's 208 divided by 12 is u squared. And I can reduce that. Let's see, what goes in? 4 goes into both of those. That's 3. 52. So u squared is 52 thirds. We'll take the square root of both sides. And I get u is the square root of 52 over 3, which is about 4.163. Now this is a big one. We use this one all the time. This is very, very often used on multiple choice questions and open response questions. This average value. And the average value is asking us to find what the average over the entire area is. So if we had an area, what would be the average amount of space under the curve? And it's very intuitive how we find that average. All we're doing, y bar you've probably not seen before. It's mostly used in statistics, but anything with a bar on top of it just means average. So y bar is the average of the y values. And to find it, we do 1 over b minus a. So we take our endpoints, the difference between our endpoints, between the integral of a to b of f of x dx. So this is the only addition. That's the only extra part for the average. Okay, let's find the average value of f of x equals x cubed on the closed interval between 0 and 2. So we have this thing that looks like this. We're going from 0 to 2. And we want to know, where is the average underneath here? What would be the average amount of space? Is it closer to 0? Is it closer to 2? Is it somewhere in between? We're going to figure that out. So to find the average, we go 1 over 2 minus 0, the integral from 0 to 2, x cubed dx. So again, this is our only extra bit. So that's 1/2 the integral from 0 to 2, x cubed dx. The antiderivative of x cubed is x to the 4th, 1/4 of x to the 4th. The 1/2 will just hang out on the outside, and we'll evaluate from 0 to 2. So if I want to be a little bit neater, I could write that as 1/8. We're going to go 2 to the 4th minus 0 to the 4th. So 2 to the 4th is 16 over 8, or 2. So the average amount of area underneath this curve is 2. The total amount of area under the curve is 16 over 4, or 4. So the average, so the total, let's see if that makes sense to what we're doing. Our total area is 4, and our average value is 2. Remember, we're going from 0 to 2. So yeah, it does make sense that if we cut 4 in half, we're going to get a 2. Yeah, that sounds like the average value. I hope that seems a little intuitive.